So let's start today's topic. My name is Juan, and today's topic is one step before game hackers instrumenting Android emulators. So first, let me give a brief self-introduction. I am Chinese, and now I live and work in Japan. I work as a security engineer in a company called DNA Corporation, which is basically a mobile game company. Personally, in private, I love playing games as well as hacking games. So this is today's agenda. Uh, Before we start, may I know how many of you have ever played or like to play games? Any kind of games? Oh, almost all of you. I'm so motivated. Uh, so first, let me introduce the background, the game cheating threat model. So we've defined three roles in the game cheating threat model: the users, the cheaters, and the vendors, aka the game developers. So for PC games, all these three roles have the full control over their PCs. They have the permission to install or run privileged code. But on mobile devices, things get a bit different. The users usually don't have a privileged access over their devices unless they rooted or jailbroke their devices. And this is the same for game developers. On the other hand, the cheaters usually own a rooted or jailbroken device. You may think, okay, then the cheaters must be the most powerful. Nothing can stop them from cheating. But this does not mean the cheaters are making profit. Actually, yes, it's true that the cheaters can hack on their own devices, but if they want to sell their cheat tools to the users, they will have to persuade their users to firstly to root or jailbreak their device firstly, which is not an easy task. So for cheaters, they think of an easy way to distribute their cheating tools. That is the emulators. Here I mean emulators like the commercial emulators like BlueStacks, Nox, and so you may have heard of these emulators. And I don't mean the AVD from Android Studio. So AVD from Android Studio are basically for x86 emulation, or which does not support APK that is built for only ARM. Or you can build a full ARM emulation in AVD, but it's super slow. So these commercial emulators like BlueStacks and Nox, they use a different technology called Houdini, which is developed by Intel, and I will introduce this further later. So for these commercial emulators, they have highly unified environment, so you don't need to tune your software, tune your cheat tools for different firmware or for different API levels, etc. And what is better is that these emulators are usually very easy to root, and they are, or some of them are even shipped with a rooted environment in advance. So this is a good news for the cheaters. So according to my investigation, the most popular cheating approach on emulators is touch simulation. So touch simulation requires root privilege. It does require root privilege, but it does not involve modification or analysis of game's binary. That also means touch simulation is a gray zone, because you can say it is cheating, but you can hardly say it is a crime, it is illegal, because it does not modify the game data directly. So, and the interesting thing is that some touch simulation engine even have some advanced function like OCR or image recognition. On the other hand, you can see cheat by hooking is not showing up on emulators. This is because game codes are usually native, and on commercial emulators, they use Houdini, as I said, to translate ARM code to x86 at runtime. So this makes it difficult to hook on emulators than on a physical, pure ARM device. So here comes my research purpose. My purpose is to enable hooking on commercial Android emulators. so you can distribute your cheat tools more easier. Uh, and this is the emulator targets I have investigated. They are BlueStacks, Nox, and Laydian. You can tell from this table the Android version, and this emulators are very much alike. They use similar Android versions and also similar Houdini versions. So maybe it's just a coincidence, but maybe not. This is not our concern, so let's move on to our next page. If you try to run a command line binary on emulators, you will find it will be executed properly. And this is because the emulators use a feature in Linux called bin format misc. With this feature, you can register a certain binary signature or magic number with a certain loader. So in our case, when an ARM binary comes to an emulator, you want to execute it on the emulator. As the slide shows, the Houdini binary, the Houdini executable will be used to load this ARM binary, execute this ARM binary. In this case, it's easy to inject your library to the target executable with RD preload feature, and thus to perform a hooking from your injected library. However, there are other methods very popular used to do hook, like ptrace. But if you try to use x86 version's ptrace, you won't make it work directly because you can't load your ARM binary with the x86 DR open. And if you compile ARM version's ptrace, because the ARM version's ptrace also will run on the emulators, but you will find you will still fail here because in fact, the ptrace is very much dependent on the registers, on architectures. So Houdini seems to fail to translate ARM's ptrace correctly to x86 version's ptrace. So this also doesn't work. But anyway, at least we have the RD preload feature work. So can we also use RD preload feature to inject your library to a Java application, not a command line application? So the answer is no, and I will show why the answer is no in the following slides. So this is a normal Java application startup process. It is well known that there is a process called Zygote in Android, and every Java application is forked from it. The basic process is that Zygote runs a loop, and when a startup request comes from Activity Manager, the Zygote will fork itself and initialize Houdini. You can see Zygote process is initialized where before launching the application. So setting RD preload environment variable before launching such an application will cause no change. Anyway, Android, in fact, it provides a workaround to enable RD preload feature when you start a Java application. So it's called the rep system property. So you can set a rep system property to RD preload equal the library you want to inject. And when you set this rep property, the start process is a little bit different. So this time the Zygote is still listening at the socket and ready to fork itself whenever a startup request comes. But when it forks itself in the child process, instead of initialize the application, it executes the app process binary with share. So of course, when you are executing a command with share, the share will firstly fork itself. So the relation among these processes will finally look like this picture. So the direct parent of the application process is actually share instead of Zygote. And this is the detail of the core stack. You will see after Zygote forked itself, a function called exec application will be called. In this function, it concatenates some command line strings and execute it with share. You can see that the app process binary is executed by share with --application parameters here. So so it looks fine that if you work, if you start the app with your app with React property, you can take advantage of RD preload. But actually, if you look carefully to this command line, so this share command is the final share command when you start an application by setting the wrap property. Uh, so look carefully. The system being shared, this binary is x86 version, and the library you intended to inject is ARM version. So this actually won't do the trick. It won't load your ARM version's binary to your target process. So in order to inject an ARM library, I'm afraid we have to investigate more about how Houdini work on emulators. So again, this is the how zygote starts. This is the common for both Android 5 and Android 4, which are used on this commercial emulators version, the AOS version. I won't go into detail of this core stack, but note that Houdini still haven't interacted with this part yet. And after the application startup, request from Activity Manager is received, the zygote fork itself, and it's here that the Houdini is initialized. From the Android 5 and from here, the Android 5 and Android 4 behave different. For Android 5, here is the Android 5 picture. Houdini is initialized by the function called, is marked red. It's called initialize native bridge. In fact, there is another stage called pre-initialize phase, but let's just ignore it for simplicity. So what's initialize bridge, what this function do is very simple. It just registers some callbacks to a structure called native bridge callbacks. So note there are two functions, very important. It's called load library and get trampoline. You can consider them as the ARM versions DR open and DR sim. So each time the Java layer want to load a library, it will call ARM library. It will call these functions to and without handle the different of architecture. So if you look at libhoudini.so file, you will find a structure called native bridge interface is exported, and some function pointers are there. So these function pointers will eventually be registered to this native bridge callback structure. On the other hand, for Android 4 version with DVM, so at that time the Android developers still haven't considered the cross-platform implementations. They didn't expect their Android will run on an x86 version device. So in this case, you have to modify the DVM's code yourself. How you modify it is quite simple. So there is a DVM load native code there, and you can insert a function called hook.dr open, Houdini hook.dr open. And what this function do is quite straightforward. It will first they call the x86 version's dr open to open the library. And if this dr open failed, it will init Houdini and use Houdini's dr open. And Houdini's dr open is marked as red. It's called, actually its name is dvm2ht dr open, and there is also a function similar to drsim. It's called dvm2ht drsim, and these functions are registered in Houdini init hook init. So this is basically how Houdini is initialized in emulators. And during my investigations, I found some interesting facts. So there are, as far as I know, Intel does not, so Houdini is developed by Intel, and Intel actually does not provide commercial license for Houdini library publicly. So as you can see, there is another emulator, very famous emulator called Genymotion, which is also super famous, but not included in my research. because it is not bundled with the Houdini when released in order to avoid the violence of the Intel license. Uh, Instead, it will hint you to download the Houdini binary yourself somewhere after you download their software emulations. So this is not efficient for users, so Genymotion is not a main cheating platform. But on the other hand, you can see BlueStacks, it is using libhoudini. It is using Houdini while released, and deliberately or not, it seems that it's trying to hide the Houdini binaries. So if you look at the reverse the libdvm.so file in BlueStacks, you can find a code like it's trying to DL open a library called lib3btrans.so, and if this DL open failed, it will tell you libhoudini libraries load is failed. It does not consistent. So actually, this lib3btrans.so is libhoudini.so, so they somehow want to hide it. For Nox, they packed the libdvm.so file, but if you unpack it, it's basically doing the same thing as BlueStacks. So next, let's go to the hooking stuff. So there are very many famous hooking frameworks existed, like Exposed, Frida, and Substrate, some typical ones. So Exposed usually is only used for Java applications for hooking, but I will talk this later to use Exposed to enable a native hooking. So, and the second one, the Exposed works by substitute the APP process, and it will load its own jar files in this modified APP process. And when Zygote fork itself, so it makes sure that all of the applications forked from Zygote will load the jar file in advance. So, and another one is Frida, and Frida is my favorite hooking framework. It's instrumentation framework. So it almost can do everything. You can use it to instrument on your desktop, on iOS, on Android, and you can use it to instrument the Java layer, and you can use it to instrument the native layer. So, but the bad thing for cheaters, they don't want to use Frida. The cheaters don't want to use Frida because Frida act as a client side and a server side. So you have to connect your PCs with USB to your device and use your PCs to control the behavior of your device. So you can't develop cheat tools by Frida and distribute it to your users easily. It will require your user to plug your USB properly and have a rooted form and have a PC. So it's not preferable for cheaters. And what's more, Frida said, the author said they won't support emulators instrumentation in a foreseeable future. It's not their priority, and this is on their GitHub's issues. And Substrate is it's also a good one, works on Android. It works by fake the liblog.so file, so every Java application will load this fake liblog.so file to achieve the injection. So, but it's kind of outdated. It only works up to Android 4.4, if I recall correctly. And if you want to make it work with emulators, you have to do some modification yourselves. So here comes my proposal. So, no, this is the normal approach for how do you do hooking. So besides the LD preload trick, you can also do hooking using ptrace, right? So the basic idea is to use ptrace to attach to your target process and call the DL open inside the target process to load your injection library. And in the injection library, you would modify the function entry point. So that's the hooking part. So on an emulator, it's only one step further to do hooking. So it's the same. First, you use ptrace to attach the x86 version's ptrace to attach to your target process, and you call DL open to load your x86 version's injection library, and inside your x86 version's library, you can load the libhoudini.so, and to find the libhoudini.so's dir open inside it, and use this dir open to open your ARM version's injection library. And inside this real ARM injection library, that you can do your hooking works. So so my implementation is based on this A method, but after I implemented it, I found there is another process. There is other way to achieve this goal. So you can utilize exposed. So exposed basically it works for x86 Android versions, and so the key point to hook on emulator is to inject the most difficult thing is to inject your ARM library to the target process. So and being aware that exposed has already enabled you to inject Java code to the target process, so you can take the advantage of this feature to call system load library inside the target process with the help of exposed. So note that the system.load library function will take care of the architecture-dependent native library. So you don't even have to know how Houdini works, how emulator works to load the ARM or x86 versions library. So you can just call it using exposed. So after you load your native library, it's successfully injected to your target process, and then you can do hooking works to inside your native library. So this is my tools, my GitHub, my tools to hook on the emulators, and it's based on the method A. I didn't make one based on method B, and the usage is as simple as hook by hook. You can pass the library and the target address to this hook by address function or hook by name function, and you can hook it. I'm going to show you a demo, but you don't expect this demo to be so fantastic, because it's on a demo game, and the demo game is basically made by our company for training purpose, and definitely I can't do a demo on a real game product. It's illegal. I got caught. So I can only perform this on a demo game. So this is the typical cute kawaii characters in Japan. Huh? Sorry. So first you are fighting the boss, and the boss SP barely subtract, and of course you lose, and this is on the emulator of the Nox emulator. So and you use ADB share. You use ADB share to connect to the emulator and play this stage again. Seems you are still losing, but you can find the result. It's actually win. So finally, this is the conclusion for today. So mobile game is getting more and more popular, as well as cheating developing, and cheating patterns change as the technique develops. So I am expecting the cheating patterns will become more popular on Android, and there are more people using hooking skills on emulators instead of only merely touch simulation, the primitive method. So, but of course, so in order to prepare ourselves as a game company, prepare ourselves for this kind of cheating, we should do some further like further work like emulator detections or doing some other efforts in the future. So and finally, game security is fun, and I'm so happy to meet with so many guys that like plays games or maybe also like hacking games. So thank you. Any questions?